Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue more on thermodynamics. We'll see some more fundamental ideas for understanding the second law of thermodynamics. Among these basic concepts for second law of thermodynamics, we'll start with what are isothermal processes, and then the path quantities that we saw in the last class, some more mathematical ideas about that, such as inexact differentials. Then we will see what are adiabatic processes. Both isothermal and adiabatic are going to be quite important to understand the second law of thermodynamics. Then in irreversible process in the last class, we saw that there is some work that is getting lost. Okay, so today we will see what is that lost work in terms of inelastic collisions. Then we will see something quite important called calculation of work for this adiabatic and isothermal processes. So that's going to be today's content. What are isothermal processes? Isothermal process means that throughout the process the temperature is going to be constant, and in this case there can be heat exchange as well as work exchange. So this is going to be different for adiabatic process. That's why we emphasize this point here. Right. In the isothermal processes, we'll first see what are reversible isothermal processes. Consider a system of let's say ideal gas with certain mass on the top in state 1. The volume, pressure and temperature are given here, and in PV space it is represented here. Then in the process that we are going to do, temperature is going to be constant and it is going to stay at T1. Right. What process we are going to do? We are going to heat it as well as remove some mass from the top. Remove the mass in such a way that the temperature is maintained constant, because as the mass is removed, the system does some work in pushing the piston up. So that work will be exactly compensated by the heat given from the bottom. Therefore, the temperature is not going to increase. If at all the piston doesn't move, you can imagine temperature will increase. The piston moves exactly at the right speed, doing the right amount of work, so that the heat supplied here compensates it, and there is no temperature increment within the system. So temperature in the final state is also T1, but volume and pressure are different. So in the PV space, it's going to be here. This is the state 2. Now this entire path, it's going to have PV equal to constant, because we say PV equals nRT and the temperature is constant. N is let's say the number of moles here is not changing for the system. Therefore R is already is gas constant. Therefore nRT, everything becomes constant in the right hand side. So that is this path, and it's called an isotherm, meaning the temperature is going to be constant throughout. And this is the work done in this process, W reversible. Now if we reverse it going from 2 to 1, then we are going to have minus W reversible, meaning work will be done on the system. Whatever mass is removed will be put back slowly, so that it follows this reversible path, and we get the work in reverse direction as well. And forward direction and backward direction, work is going to be same in magnitude but opposite in direction. One is work done by the system, other one is work done on the system. Right. In irreversible isothermal process, we are going to do the same thing again, but here we are going to remove the mass in one go. One third of the mass is removed. Therefore, the system goes to a new state, state 2, but the temperature at the final state is T1. The heat is supplied in such a way that the temperature T1 is achieved. But we don't know in between what happened to temperature. We measure temperature only when the system reaches the equilibrium and stays calm. That is when we measure the final temperature, and we make sure that enough heat is supplied and the temperature is maintained as T1. If that is the case, we are going to go to state 2 like this, in this kind of path, and W irreversible is the work done in this path. And when we put back the weight, W forward will not be equal to W backward. We saw this. More amount of work is required to compress the gas to bring it back to state 1. So therefore, more work has to be done on the system. Now, starting from the first law, delta U is equal to Q minus W. And for reversible process, we can write it like this. For irreversible process, we can write it like this. And what we know for sure is delta U is going to be same no matter what is the path, whether it is reversible path or irreversible path. As long as we go from one initial state to one final state, delta U is going to be same because it's a state property, right? And these two formulas are there for us to understand something about this Q value and W value. So since delta U is going to be equal, this right hand side in both these equations, they are also going to be equal. Let's bring them together like this. That means in reversible process, we had this much of work done. In irreversible, we had lesser amount of work done. If work done is different, this W reversible and W irreversible, if they are different, then obviously for this equality to be held, these two values, Q reversible and Q irreversible, also should not be equal. So W reversible is not equal to W irreversible. Therefore, Q reversible is not going to be equal to Q irreversible. This is an important conclusion about these path quantities, because you see different amount of heats can be given, different amount of works can be done, but the final state is going to be same and the delta U is not going to be different between the two different paths. Okay, so that's the reason why we call them path quantities. We saw about that in the last class. And what are inexact differentials? We'll see that. You see, delta U, we said between two different states, we have an exact delta U. The initial state and final state have a fixed U values. Therefore, delta U is an exact quantity, the difference between the internal energy of two states. But for Q, we can't say an exact delta Q. It doesn't exist between two different states. We can give any amount of Q, extract any amount of work so that we achieve the same state change. So in that case, there is no exact delta Q. If that is so, then Q is what will be used instead of delta Q. Similarly, in the differential form, we will use this squiggly kind of delta Q is used instead of the dq, which is used for exact differentials. So this is the reason why all path quantities will be represented using this kind of symbol rather than dq. So that is called as inexact differential. And now you understand why we are using this kind of thing, because there is no exact differential differential quantity for this Q value. Okay, so now we will consider reversible and irreversible processes together, and what happens to Q and W we can sense from this slide. Let's say in the reversible process, we go from here to here and come back from here to here. So both are reversible directions, going forward and coming backward through the same path. Okay, that is reversible. In that case, the work done is equal. Therefore, the Q values also are going to be equal. Whereas in the irreversible case, we go like this and like this for the expansion part, and for the compression we go up and come like this, right? So this particular this part is forward and this part is backward. In that case, W forward and backward are not going to be same. Q forward and backward are not going to be same. If that is so, for in the surrounding, what happens? Let's track system and surrounding together and think about what kind of state changes will happen in both. Okay, let's say initial state for the system is state 1 and for the surrounding is state 6. When system in the reversible manner, if system goes from state 1 to state 2, surrounding goes from state 6 to state 7. And when system comes back from state 2 to state 1, surrounding goes back from state 7 to state 6. So there is no change in surrounding after this reversal. Whereas if we do the irreversible process, we'll see that as we go from state 1 to 2, system does not go to state 7, it goes to state 8. And when system comes back from state 2 to state 1, surrounding goes to yet another state, state 9, which is definitely not state 6. So it doesn't come back to original state. after this entire reversal. So based on this, we can classify or define reversible and irreversible process. This is another way to define them. A process that leaves no trace of change in the surrounding if reversed. That is what has happened in the reversible case. So that is reversible. Whereas a process that leaves a permanent change in the surrounding if reversed, that is called as irreversible process. Okay, this is one way to define reversible and irreversible. Now we saw that isothermal process already. Now it's time to understand what are adiabatic processes. In adiabatic processes, we don't have any heat exchange. There can be work exchange between system and surrounding, but not heat exchange. Okay, the first process we are going to understand is reversible adiabatic process. So we are going to put this thick white color line here, showing that there cannot be any heat exchange between system and surrounding, right? Then we are at initial state 1 here, and if we start doing this process of expanding the gas, so we said there is no heat that can be supplied, so let's just remove the weight from the top and expand the gas. So this entire process is adiabatic in nature, meaning no heat goes out of the system as well. No heat comes in, no heat goes out. Now it is going to reach this final pressure of P3. So this is the final state, V3, P3 and T3. Now let's represent that in the PV space. This is P3, V3. So we go from here to here in reversible manner, meaning removing the mass very slowly. Right. The work done is the area below this. Now let's see about irreversible adiabatic processes. The irreversible adiabatic expansion happens like this. So within this adiabatic wall, there is no heat that is permitted to go outside. The expansion happens and this is the final state, V4, P4, T4. And let's track where is it. This is state 4. Fine. Compared to state 3, which was achieved in the adiabatic reversible expansion, here we are seeing a slightly higher volume. But since the pressure on top, the load on top is same, the pressure is going to be same in the final state. The P4 and P3 are going to be same, whereas the volume in the state 4 is going to be higher than the volume in state 3. So more volume is achieved in this case, and that is because the temperature also is higher. The temperature at state 4, T4, is higher than the temperature achieved in the reversible adiabatic expansion. So this is the kind of work that we can calculate. Compared to reversible process, it will be lesser, and some amount of work is lost as heat. That heat stays inside due to adiabatic boundary. Okay, that's the reason why temperature increases. Of course, something may be slightly vague now. Once you understand what is inelastic collisions, you will understand this better. Now the point is the gas expands and there is some amount of work that is lost, and that lost work is in the form of heat, and that heat increases the temperature here because that heat cannot escape. It increases the temperature of the system. Therefore, system goes to a even higher temperature and correspondingly higher volume. So what is this inelastic collision that I am talking about? So kinetic energy gets converted to heat when inelastic collision process happens. Think about a ball falling on a floor. Okay, it slowly, the maximum height to which it can jump comes down and it eventually reaches this rest state. What happened is, compared to the initial state, the floor and the ball get slightly heated up. Okay, we can't sense it, but they all get slightly heated up. This is where the kinetic energy goes. Okay, the ball, when it was moving, there was a kinetic energy to it, and that kinetic energy vanishes now. So as we know from the law of conservation of energy, the first law of thermodynamics, energy cannot be destroyed. So where is this kinetic energy going? This kinetic energy is getting converted to the motion of the atoms in the floor and the motion of the atoms in the ball. Nothing but heat. Okay, so that kinetic energy for the entire body is now the kinetic energy of motions of particles. We call that as heat. Okay, so everything is slightly heated up. This is what happens when kinetic energy becomes heat. This is a result of inelastic process. Inelastic in the sense When two bodies collide, they don't, let's say two bodies are colliding and they don't repel with the same velocity. Okay, there is some kind of a velocity compromise, the velocity is decreased. What happened to that velocity, the energy that was there before? Why can't they go back in the same velocity? The reason is, in the collision there may be some heat generated, some sound generated, some light generated. All of them cause the collision to be inelastic in nature. They're not elastic anymore. Okay, they go out with slightly lesser amount of energy, and we call that inelastic collision. Think about the two cases where we expanded the gas in the reversible and irreversible manner. At least the very first step, if you see, the moment the load is removed, the gas expands. The more important thing to observe is the piston moved at a velocity, right? When the piston moved at a velocity, as it stops, what happens? All the kinetic energy of motion of that piston, where has that gone? That has gone into heat. It has become heat and it is getting spreaded through all the solid parts, whatever we see, the piston, the load, the stopper, the walls of the container, and the system inside, the gas inside. Okay, to everything, that heat gets dissipated. So everything gets slightly hotter. This is what happens when the piston moves and stops. So there is a kinetic energy which has now which is now converted to other forms of energy. So heat is the form of the energy to which it is getting converted. Whereas in the case of reversible, it doesn't happen so, because if you remove something, a small mass, there is hardly any velocity developed. That is the point of moving things stopping. There is nothing like that here. So therefore, the kinetic energy loss or kinetic energy itself is not there. So what happens in this kind of process is, the piston actually moves more load. There is a more amount of load. Almost the entire load is still there, right? So it is moving, doing more work. Okay, in the reversible process, that exact work is what we are losing. Okay, we are allowing the piston to move fast. That is not going to give us a work done. Okay, work may be done faster, but it's a small amount of work. Okay, that's the problem with the irreversible process, right? Okay. If the piston moves at a velocity, it has a kinetic energy. Of course, any movement is going to be associated with the kinetic energy. And when it stops, the kinetic energy is going to change to heat. Then it spreads to all the solid parts and the gas. That corresponds to work loss. In the reversible process, there is no velocity for the piston and no kinetic energy, and there is no work loss. So it's a very subtle and interesting idea. Now, irreversible adiabatic process, compression we will see now. Let's put back this mass and see whether we get it back to original state. So this is what happens. The final state now is V5, P5, T5. We call it state 5. Definitely it's not state 1. What happens is, the gas compresses and it comes to this. The gas gets compressed and it comes to this state. The system could not be restored to initial state. Why? P5 is equal to P1, but V5 is not equal to V1. It is greater than V1. The reason is this. So this is the kind of work done in this process. This much extra work is lost now. Meaning, if you put the piston, the mass back, it could have come back and did this much amount of work, the mass that we have put back, but that much work could not be done. There is a problem here, because inside the things are getting hotter. Yeah, the heat stays inside due to the adiabatic boundary. Therefore, the gas is becoming hotter now. Yeah, so temperature in state 5 will be higher than temperature in state 1, which corresponds to the higher volume in state 5. So let's do the calculation of work in these two processes. Okay, adiabatic and isothermal process. In the adiabatic reversible process, we are going to go from one state to the other state. There is no heat exchange here. And P1 V1 becomes P2 V2. This is the area under the curve. W is going to be integration V1 to V2 PdV. So P P here is not constant. So function for P in terms of V is what we need. What do we do? Equation of state for ideal gas we can use now. PV equals nRT we have. So can we get P as a function of V now? Yes, P is equal to nRT by V. But what about this temperature? Temperature, is it constant here from here to here when we go? This is not an isothermal process, this is adiabatic process. So temperature is not constant. That way this equation becomes a tricky thing to use directly here. If we try to replace this T with something else, in terms of let's say P and V only, then we can talk about doing the integration and all, right? So let us see what we can do. We know currently we know this del Q is equal to du plus PdV, first law. And since there is no heat exchange, del Q is going to be 0, right? So now this equation is 0. Now this gives us some clue. We know U is related to temperature, right? And if through that, if we have something here also in terms of temperature, we can keep temperature on this side, take everything to the other side and think about temperature being something. So that is what we are going to do now. Let's see. U equals 3 by 2 nRT. We have derived this. Internal energy is merely a function of temperature for ideal gases, and du by dt if we want to do so here. So if we differentiate this with respect to T, we get 3 by 2 nR, and du is equal to 3 by 2 nR dt. So for this du we got something in terms of temperature now, and this 3 by 2 nR is we can change it. 3 by 2 r is Cv, so n Cv dt comes here. So del Q is equal to, in place of du we write nCv dt plus PdV we can write nRT by V dV. Instead of P we are putting this entire thing. Now we got both the terms in terms of T, and that is equal to 0, right? Let's start with that. Okay. So this thing is equal to 0. We can rearrange it like this. Then dt by t, dv by v are there. That is going to be natural log of t2 by t1 and natural log of v2 by v1. And this, if we rearrange, we can write this entire thing is equal to 0. And therefore, the natural log, if you remove, the right hand side is going to become 1. So this is equal to 1. So T2 power Cv by R into V2 is equal to T1 power Cv by R in V1. It means that this combination of Tv is going to be a constant. So T power Cv by R into V is going to be constant. If that is constant, we can rearrange it, and in place of T we can put Pv by R from gas law, ideal gas law, and we can write this. So if we carefully rearrange this part like this, we will see that this side is going to become some other constant. So Pv power Cv plus R by Cv is equal to C. So Cv plus R we can write it as Cp. So Pv power Cp by Cv is equal to constant. Therefore Pv power Cp by Cv can be written as gamma, as we derived in the last class, which is equal to a constant now. So if this is so, then P in terms of V can be written like this. Right? So now we got an equation for P in terms of V. We can use this and do the integration. Substitute into V1 to V2, P dV. We'll get the work like this. So here P is equal to Cv power minus gamma. And if we integrate, we are going to get this. Upper limit and lower limit are substituted. So C can be replaced with P2 V2 power gamma from this equation. C is kept this side, V is taken to that side, PV power plus gamma will come. So that is here, PV power plus gamma. And we have seen that P2 V2 power gamma and P1 V1 power gamma, both are C. Okay, so that's what is used here for our convenience to simplify it further to get into this form. So this is the work done now, P2 V2 minus P1 V1 divided by 1 minus gamma. This is the work done in the adiabatic process, the area under this curve. So this is one important conclusion. And in adiabatic process, Q is equal to delta U plus W as far as first law is concerned, and that's going to be 0. Therefore, if at all there is a work done in the adiabatic process, where from that energy came, where from this mechanical work came, this mechanical work came only by reduction in internal energy. So the gas must be getting cooler to perform this work. Okay, that's the meaning of it. Right. Let's see how to calculate work in isothermal reversible process. So this is the area under this curve. It's fairly straightforward to calculate. We want to do this integration of V1 to V2 P dV, and P is not constant. We can use a function for P in terms of V, and ideal gas equation is going to give us PV is equal to nRT and P is equal to nRT by V. More importantly, the temperature here is constant because it's an isothermal process. So nRT by V, you can essentially see that V is the only variable. Therefore, we can use it directly into this equation and integrate it with respect to dV. We get this nRT natural log of V2 by V1, that is the work done in isothermal process. Fairly straightforward. The heat that is going in this isothermal process, what happens to this Q? What happens to this Q that is coming in? Does it change the internal energy? Does it do the work? Does it do both of them? The answer is no. The delta U is not even there because it is an isothermal process and delta U is a function of temperature. We don't see any delta U here because all the Q that is given is converted to W. Carefully we have supplied heat and made some work done by the gas. Therefore, these two are compensated and the temperature remained constant. That's the meaning of isothermal process. Therefore, the internal energy remains constant in isothermal process. So all the Q that is given is now converted to work. Okay, so this is a summary of the two equations that we got for the work done in adiabatic reversible expansion and isothermal reversible expansion. These two are going to be quite useful for us when we understand how engines work and what is the efficiency of engine, and from there we will derive ideas such as second law of thermodynamics. Thank you. I hope the lecture is useful. See you in the next class.